So in this section, I am going to explain about RNN. So what is RNN? It is the recurrent neural network, and especially the RNN can be used in NLP. And what is the RNN as the language model, and what would be the NLP tasks with the RNN, and we are going to look at some RNN issues and some RNN variants. And at the end, yeah, we need to check the code. So let's do the analysis of the code. RNN, or we call it the recurrent neural network. We call vanilla. So the word vanilla, it means that this is the original RNN, or the common approach in RNN. We call it, this is 1-to-1, because we have one input and there will be one output. So in RNN, we have one input and one output, and we will have one matrix to be the factor in order to create the weight in this RNN. So we will do the step by step. It means the iteration will be from the iteration 0, from iteration 1, iteration 2, until several steps. And after we get the proper result, or after some epoch, or after some iteration, then we will finish and show the result. We call it, this is until the time t, because the iteration can be different based on the data set, based on the running time, and based on the stopping condition. So the RNN means we have some hidden state. So the hidden state, it will be updated. So we can process a sequence of factor x. So usually we refer x as the input by applying the recurrence formula at every time step. So we are going to apply this formula every time step. So the every time step, as you may know, we have like time 1, time 2, time 3, and so on until it will be the time n. And the formula will be something like this. The ht, we call it, this is a new state. And the ht will be determined by a function. A function here, it can be the activation function. In the deep learning, you may learn some activation function like sigmoid, or maybe you know that the activation function is about the review, or maybe there are some other activation functions such as tangent, and so on. So the activation function can be any function, and we have the parameter W. The W is the weight that is produced during the neural network. And we are going to do this one on the old state. And for the every states, we will check the input. So it means we have x here, and then the old state, let's say this is the h0, it will determine the h1. So the new state, which is the H1, it will be determined from the H0 and X in a particular T. So we can process the output. The output for every RNN means that we can process again after we have the X again by applying the recurrence formula at every time step. So the Y or the output, it can be calculated something like this formula. We have the Y, which is the output at the time t, and then we have the function. So it can be tangent, it can be sigmoid function, it can be ReLU, and etc. For the state H and the particular Y, where we know about the new state or the current state. So we have the yt, this is y, it equals to the function of w, which is the parameter, and it is based on the hidden state in that particular time. So we can see something like this one. In order to calculate the hidden factor or the h, so we have the ht equals to the function ht minus 1, and we want to look at the input. So for every of this ht, just for example, we have the tangent value, so the tangent function. So this is the tangent function. And this tangent function, it will be calculating this formula. So the weight in that particular h, it will be multiplied with the ht minus 1 plus the weight in the particular t of the previous x in the particular time h multiplied by the input. So what does it mean? So let's see with an example. So the output, the yt, will be based on the f or the function of the particular weight multiplied by the h at the particular t. We can see something like this. We have h0 and we have x1. So there will be a function here, and this function will determine the x1. So we have the input h0, we have the input x1, and it will create the h1. And we have the h1, so the h1 will be the input for the second round, and it will be combined with x2. It is to create the next hidden state. And then after we have h2, it will be combined with x3, and we have a function, and it will create the h3, and so on. Okay, so that's why we call this is recurrent, because once we have a formula here, it will be updated using the same function, but we have different value. So using the same function with different value, using the same function with different value. That's why we call it this is recurrent. So every time it will be calculated using the same width matrix. So reuse the same width matrix at every time step. For this one, for the first, we may have a particular weight, and we use this weight to calculate the next hidden state. And after that, we will again do the same with the same weight. So with the same weight, we calculate the x1 and x2 to produce x2. So we have again the same way to calculate the input from x2 and x3. And using the same way, we calculate again from the particular x time until the xt plus 1 and so on. We will reuse the same weight. The weight is the same. So that's what we call as the vanilla recurrent neural network. So let's see with one example. At first, for the step in the RNN for NLP, we will initialize the hidden state of H0 and other parameters. Now, let's say I'm not concerning about the parameters. Let's say just the parameters is 1. And we will compute the hidden state, which is the HT. HT is one step. So usually we have the step plus 1. So if we start from 0, then let's do the H1. If now we are in the t equals to 1, then let's do the t plus 1, which is 2. If now we are in the t equals to 2, then let's do again the calculation, compute the h plus 1, which is h3. And then optionally, you can compute the output. So it depends why we need to calculate the output. So we will take a look some of the variant. As the hidden state from one step to the next. So we have H1, and then we have the formula, and then we have H2. And then we have another formula, and then we can create H3, and so on. Process the final hidden state or sequence of output as needed for the task. So it depends whether your task is regression or classification or sentiment analysis or text generation and so on. So we can do with the final hidden state in order to complete the particular task. And we need to calculate the loss. So yeah, I'm not going to explain about the loss. If you join the deep learning class or if you join the data mining, I hope that you already got some information about how to calculate loss. And we will apply the back propagation through time. So in RNN, we have this one, back propagation through time, or BPTT, to update weights and biases. So let's see with this example. I have a sequence. I love NLP. So for the vocabulary size, let's assume each word is encoded as one hot factor. One hot factor means we have I, love, NLP. And let's suppose we have this one 1, 0, 0. So I know that in this X, I want to consider only the word I. In X2, I have 0, 1, 0. So I want to focus on the word love. And then in the X3, let's suppose I have 0, 0, 1. So I'm going to focus on the word NLP. Then we can have like this one, x1, x2, and x3. So let's suppose we have the input to hidden width matrix. So the input to hidden width matrix, it means the first matrix that we want to consider, or the width, as you know, the width will be the same for every of the formula. And we need to have the hidden to hidden width matrix, or sometimes we call this is the initial edge. And in the neural network, there will be bias. Okay, so let's assume the bias is 0.1 and minus 0.1. For the initial hidden set, let's make it as 0 and 0. So the H0, it starts with 0 and 0. Now we will have the structure, which is H0 and X1, and we are going to do a formula to determine the H1. So using this information, okay, so this is the H0, and then we have the X1, X1 is this one, and we apply the formula that we have. So the first step is the word I. So the input factor X1 is 1, 0, 0. We use the hidden state calculation that we have before. So based on the formula before, we have the HT equals to a function given any weight, and we are going to use the HT minus 1 comma x1. It means I want to know what is the hidden state in the previous time, and I want to use the current x. So let's suppose I use the tangent function. So the tangent function, I'm going to put all the information from the from this one. So it means I would like to calculate the width multiplied by the x1, okay, the width multiplied by the x1 plus the particular width for the hidden multiplied by the hidden value on the previous states plus the bias. So in order to calculate the WXH x1, you know, we have the matrix. This is the matrix of the weight. This is the matrix WXH, then this will be always the same for every step. And we will multiply with the data, or this is the x1. And we have the matrix 2 by 1. So 2 rows and 1 column. After this, we will compute the hidden state. The hidden state, we use the WHH. So this is the width to calculate with the head. Because the H0 is 0, 0, every value multiplied by 0 will be 0. So the WHH multiplied by H0, it will be 0. For the bias, we know from the neural network, in the neural network, we will just update the bias for the next steps using the formula. We have the WX1 here, and then the WXX with multiply by H0 plus the bias. Then this one is from here, 0, 0 from here, plus with the bias that we have. So this result will be a matrix with 2 rows and 1 column. So the H1 will be a tangent of 0.6, 0.7. And after we have this with the tangent value, so you can convert. Now the final result of the H1 is 0.537 and 0.604. So this is the H1. So we have the H0, we put into the formula with X1 and we get H1. After we have the H1, now we move to the second stage. In the time step 2 or the next round, let's use the word love. Then in the word love, we have X2, this is 0, 1, and 0. Again, using the same formula for the hidden calculation. Now we are going to calculate the H2. We are going to calculate the H2. So the H2 is the result from H1 multiplied with the particular weight and X2 multiplied with particular weight. So X2 multiplied with the weight that we have and H1 multiplied with the weight that we have plus the bias. Then using the weight XH, so the weight is the same, and we multiply with the X2. So X2 is this one, 0, 1, 0, 0, 1, 0. And using the matrix multiplication, we got this value. After we got this value, then we want to multiply the H1 with the weight. So the weight is the same, but the H1, it is the result from the H2 with X1. So we use the value from the previous steps to calculate the WHH multiplied by H1. So we get this result. We put the bias, so it means this value is here, plus this one is here, plus the bias, this bias. Then we can get the result. This one is here. We use the tangent function. Then the result of H2 is this one, 0.0746 and 0.1964. This is the H2 result. And let's do on the next step. On the next step, we have the word NLP. So the X3 is 0, 0, 1. And again, we need to calculate the hidden state calculation. The hidden state calculation, it means we are going to find H3 by using the tangent formula we are going to use the X3 and multiply with the hit in the H2 and plus the bias. So with the same matrix, this one, we are multiplying with the input. So we got the value here, minus 0.6 and 0.4. This is after we multiply the width with the input. And then we want to consider the hidden state. So the hidden state will be multiplied with the width. The H2 value is this one. So we use the H2 value and multiply with the width for the hidden state, and we got this result. And after we have this result, again, we put all of them into one formula. So this is the result from here, this is the result from here, and this is the bias. And we got the result like this. At the end, because this is a tangent function, so we need to convert this value into a result with the tangent formula. So after we do with the tangent formula, so we got this result. Then this is the value for the H3. Okay. Because we already did with every word in our text, which is the I love NLP, then we can get. So after processing the entire sequence, we have the following hidden state. So this is the H1, H2, and H3. Okay. So after we have this hidden state, what should we do? So after we have this hidden state, we can do more with, for example, check the output. Can do the output generation for Y1. We can do the output generation for Y2. And we can do output generation on Y3. So for this output generation, I will focus on the next week material. So to this class, I will focus on the RNN and the deep learning stuff. So in the RNN itself, there are some processes. Okay. So the one that you learned before, it was only for one-to-one. For one input, you can produce one output. So this is input, and you can produce one output. But there can be one to many. It means you will have one input. The input is only one, but the output will be more than one. So for example, you have an image. So you will put one image, but the result is a sequence of words. So if you put one image, maybe the result is an apple with a cup of tea. So an apple with a cup of tea. Then it is many. The result or the output will be more than one. So we call this is one to many. We have many to one. Many to one means the input, there are many, but the output is only one. For example, action prediction or activity prediction or activity recognition in the INSEE. We have a video, a sequence of video frames. For example, if you put a YouTube and then you want to recognize whether the person is doing soccer or baseball. Then you put a video frame, so there will be multiple frames, and then you will determine what is the activity. So the activity will be only one. So we call this is many to one. Or we can have many to many. It means there will be many input and there will be many output. However, the sequence is different. In the first step, the sequence, maybe this is time 0, time 1, time 2, and the output started from time 2, time 3, time 4. Okay. So this kind of many to many, maybe the example is we have a sequence of window frames and we are doing the captioning. So the captioning is not only one single class, but it is a text. For example, soccer, playing soccer in the green grass. Then there will be more than one output. And we can have many to many with this kind of structure. So whenever we have an input, for example, I have a video, then you directly classify based on the frame level to a particular class. You have one input and then you directly classify into a particular class. You have a frame of a video and then you directly classify into a particular class. So those are the variation of RNN. You can use not only one input and one output, but we can have one to many to one, many to many with this structure, and many to many with this structure. Let's have a break. I will continue after the break.